See if anyone's coming on. One person so far. All right, I'll get started. So welcome back to STEM Online Academy. My name's Jason, for those of you who don't know. Today we're going to be doing something very interesting. We're going to be doing a master class on contour integration. Okay, we're going to get deep into contour integration, mainly the conceptual parts of contour integration, okay, because it's very important for your mathematical toolkit, okay? So those of you who are in math, physics, or engineering, this is a must-see lecture, okay? So we're going to take off with that, all right? So it's going to be a concept first, pretty much a deep dive into contour integration, okay? How it works, why it works, okay, and how complex analysis um, can help us solve real integrals in real time, okay? Actually, not just real integrals, but almost these like seemingly impossible integrals. Impossible. I put quotations there because non-elementary methods would be able to solve them unless you are able to use contour integration. Okay, so that's why it's important. All right. So today we're going to do something really cool. Okay, today's Wednesday. All right, and it's going to be focused, rigorous, and intuitive. Okay, so stay tuned. All right. For those of you who don't know me, again, my name is Jason. This is STEM Online Academy. We are a advanced math and physics and technology STEM channel, right? Pretty much the real hardcore sciences, okay? Where we try to help undergraduate students strengthen their critical thinking and mathematical intuition, okay? All right, so that's the goal of this channel, right? To develop a sixth sense for doing mathematically oriented problems or mathematical physics problems, okay? Now, as long as you have a background in calculus and linear algebra, like a strong background in calculus and linear algebra, you'll be fine with this, okay? So let's get started, okay? So we're going to be looking at the following, okay? So let me share the screen, sorry. All right, so let's share a screen. Okay, so I'm going to share a screen. Okay, so just 1 second. I'm going to share my screen. Okay. And we're going to head to the whiteboard. Okay. And we're going to get right to it, right? So the live show again, right? Residue Calculus Masterclass. I had another live show on residue calculus. So if anyone's in here who's watched my past live show, you're probably asking, why am I making it again? First off, I didn't do it on a good day. It's good to research what days the live shows are most effective. Didn't get an audience that day hardly. So probably most of you who are interested or whatever or didn't know weren't able to see that live show at that particular time. And even if it was after, you probably weren't able to attend it for A or B reason. Okay. So I'm making another master class on residue calculus. So that was one of the reasons, right? Because it wasn't on a good day. Usually the volume of people that come in on that day wasn't good. I should have done more research. That was my mistake. And number two, residue calculus is a bit annoying. Okay. So what do I mean by that? What do I mean that residue calculus can be a bit annoying? Well, it just means that it can be it can be a bit tricky conceptually to determine what type of parameterization you have to use for your contour, if that makes sense. Okay. So it's very important to choose the appropriate contour, okay, in order to do your contour integration. Okay. So again, I'm making this live show specifically because of the fact that I feel like there needs to be more of an intuitive and conceptual discussion on contour integration, because it's quite often there's common problems that students have with it. Okay, I'll talk about the common misconceptions when it comes to contour integration. That's the whole point, right? The whole point of my live shows is to help you solve conceptually whatever problems you have. Okay. All right. And don't forget, you can ask me questions. Okay. Anytime during it's a live show, right? All right. So you can ask me any questions during the live show. That's completely fine. Okay. Don't be shy. Don't be in the background there, and just type something in the chat if you have an issue, if you need help with anything. I'm here to guide you on the subject at hand, or a highly related subject. And also it's because I want to discuss this because it's from my book, Advanced Integration Techniques. Okay. So number one on today's menu, yes, we're going to talk about why residues matter. Okay, number one. All right, so that's number one on the menu. Number two, we're going to look at something called poles, residues, and singular type of behaviors, and what they mean exactly. Okay, so poles, residues, and singular type of behavior. Okay, for contour integration. Number three, we're going to look at our very first contour integral. Okay, it's going to be this type here, the most basic type of contour integral. Okay, it's by the contour integral is a loop integral. That's why I put a loop there, dz over ZMSA. Number four, why the integral equals 2 pi, like why that integral, right? Why this expression here equals 2 pi that I'm highlighting, okay? Number five, real integrals via residues. Pretty much number 5 and 6, almost the same. I don't think I need to write 5 and 6. Okay, so 5 and 6. All right. Number 7, we're going to be closing the contours and decays. All right. Number 8 will be an interpretation and common student mistakes. Okay, this one is very important. Probably the most important. Let me see here. Number 2, 5, and 8 are the most important. 2, because I have to introduce you to the theory. I have to. If I don't, otherwise you don't understand what's going on. So the theory is very important. Okay, I have to keep reiterating that for math. If you don't know the theory, you're not doing math correctly. Okay, like real math. Okay, so number 8, we're going to talk about the interpretation and common student mistakes when it comes to contour integration. Okay. When I was a student, I had some trouble with it, and then I mastered it at some point. I had one professor that helped me understand contour integration deeply. So I managed to really, really, really understand it at a conceptual level. But at first I was making mistakes. So I know some of the common student mistakes when it comes to this. And then number 9 will be live questions and answers. Okay. So yes, any questions or answers you have after. All right. So let's see if anyone is in the live show right now. Okay. All right. Okay, so let's get to number 1. So what are residues? Why they matter? Okay. Now a residue, okay, residues are critical because they're pretty much, I wouldn't say, yeah, shortcut is a good word. I would say that, yeah, residues are not just a shortcut for evaluating advanced integrals, right? But they give you almost like they just happen to give you a very good getaway to evaluating complex integrals. So what I mean by that is that you can almost cheat, but without cheating, if that makes sense. Because when it comes to doing residues, you're able to learn certain types of methods that you're not taught in when it comes to elementary calculus. Okay, right? You don't learn residues in elementary calculus, but this is another method that can help, right? Another method that can help for solving advanced integrals. So this could be really handy, especially for those of you who are like in science. Like when I mean science, I mean physics and engineering. Looking at residues and contours is very important. Okay, because you guys have to use integration. You guys use integration more than math majors, actually. In math, we just go directly to very rigorous theorems and we try to prove them. We don't use the integration like computationally, but you guys need it more than us. So this will be handy for you guys. Okay, so shortcut for evaluating complex integrals. Instead of performing difficult parameterizations, contour integration does involve parameterizations, but it's not quite the same parameterizations that you may be thinking. Okay. Anyone have questions? Who's inside? Okay. Anybody? Let's see if anyone is coming in. Anyone at all? Okay. Just want to see if anyone's going to be in. This is a good time. It's 8:57. Again, don't be shy. You can come in, and as long as you have a interest in mathematics, and you have a foundation in integral calculus, you'll just be able to learn what I'm talking about. It's just a continuation of knowledge, right? Continuation of building up your mathematical toolkit. Okay. So I'm pretty much talking about specific methods when it comes to integrals. Okay. Once again, from my book, Advanced Integration Techniques. All right. So let's continue. Right. So not only instead of performing the difficult parameterizations, okay, so it's not just parameterizations. Okay. We use something else that's really important in contour integration, sorry, and that's called the residue theorem, right? This is like the bulk, most important theorem in contour integration. I need to highlight it. That's how important this damn thing is. Okay, let me highlight it. Okay? I'm going to use red here. The residue theorem. I'm highlighting this phrase here because it's so important. Okay. If anyone comes in, pay attention to the word that I'm highlighting. If you know it, please offer your input. If you don't know it, just say I don't know in the chat. And if you do, like you've learned about it, but you conceptually are still stuck on how to use it, please ask me questions. Okay. All right. So it's a shortcut for evaluating complex integrals, right? That's why residues are very important, okay? Right. So we're going to look at those in a second, okay? Well, we won't look at examples. I still have to go through the theory, all right? But don't worry, there's also going to be very interesting drawings, right? And simulations coming up, okay? That are very, very important, all right? So let's talk about... I might do something here. Let me go to the next page if there's something here. I'm going to talk about, I didn't put this in our menu today, but if I leave out these words, then these equations mean zero. They won't make sense to anybody, right? Okay, so I have no choice to discuss some nomenclature and some terminology, okay? Linguistically anyways, because if I don't, this does not make any sense, okay? So we need to talk about it, okay? And those words I'm going to bring up is called branch points and the branch cuts, okay? So let me talk about branch points and branch cuts, unless there's anyone who wants to ask questions, okay? Just 1 second. Sometimes these things are annoying. There we go. Yeah. Sometimes you have to zoom in. Right, zoom in on these you can lose your pages sometimes. That's an annoying thing using this type of software for YouTube. But anyways, all right. Anyone have questions? We have questions. Okay, so yeah. Okay, so I think we're about it's about time to talk about what a branch cut is. Okay, so what is a branch cut? Okay, so branch cuts. So let me talk about branch cuts and branch points. Okay, so I should be saying, yeah, poles, residues, theorems. Before getting to that, I should be talking about branch points. I'll call this number one prime. Okay, so one. We got one prime here. Okay, so one prime. What are branch points and branch cuts? Okay, so what? So let me go over here. Is what are branch points and branch cuts? Branch cuts. Let me go over here. Branch cuts. Branch cuts. Cuts. And see if anyone's in the audience who's asking questions. Sometimes they pop in. That's another thing too. For those of you who are new, I might go back and forth from the whiteboard to the live chat because I can't see anyone in the live chat if the whiteboard is up. So I go in and out of the whiteboard to the live chat. Okay. So what are branch cuts and branch points? Okay. So branch points. What are branch cuts and branch points? The branch cuts and branch points. So what are they? What are branch cuts and branch points? Branch cuts and branch points. Okay. Anyone know what a branch cut or branch point is? I'm waiting for you guys to engage. Remember, it's a live show. So I want to make sense for me to keep blabbering. I need you guys to offer input on the definitions that I'm talking about. Okay. Right. So please offer your input on the definitions. Okay. Because I don't want to blabber all the time. So what are branch cuts and branch points? Even if you don't know, you take a guess. Branch cuts and branch points. Come on, guys. Okay, so if you guys don't know, that's okay. I'll put it down here. Okay, so definition of a branch cut. So branch cut. So definition. Let's call UDEFN and 1 on branch cuts. Branch cuts. Okay. A branch cut. So let's put it over here. A branch cut. Okay. Is a cut. Now, don't get this confused, right? Don't worry, they're not Dedekind cuts, okay? I don't like Dedekind cuts because they're extremely difficult. So don't worry, we're not talking about Dedekind cuts. We're talking about branch cuts, right? And I'm no expert on Dedekind cuts, but I am an expert on branch cuts, okay? So branch cuts is a type of cut. I'm putting it in quotations. Is a type of cut, okay, which is used for multi-valued functions. Let me see if anyone's coming in. It's for used for multi-valued functions, right? Examples, for instance, let me look at some examples. Bring up some examples. Example EX, for example. Okay, if you had square root of Z, okay, so you have square root of complex number Z. All right. So, for instance, if you have square root of Z, okay, or if you had another type of function, log Z, etc. Maybe you had a fractional exponent Z to the m over n power, where m over n is an exponent, right? These are examples of multivariable function, multi-valued functions, okay? And the point of the branch cut is to make the multi-valued function a single-valued function, okay? It was used for multi-valued functions, and to then, right, and put over here, and to then convert to then convert them to single valued functions. Okay, so single valued functions, from multi-valued to single valued functions. That's what a branch cut is. You single valued. Probably should put this as a different color to emphasize what I mean here. It's to single valued functions. Okay, to single valued functions. Okay, single valued functions. Single valued functions. Valued functions. All right, so that's the point of a branch cut. Okay, branch cuts are exactly for that. Okay, to go from multi-valued functions, convert them to single-valued functions. Okay, so for instance, root Z, right? Right. If you look at root Z, you know that it's a multi-valued function. It's input, output, all that stuff, x and y. Okay, it's a root function. Okay, and pretty much here with the branch cut, right? By the way, a branch cut is a type of curve, right? For those of you who don't understand, right? So any type of curve, right? Not any type of curve. Let me be specific. Let me correct myself. A type of curve. That's what a branch cut is. Okay. So let me go over here. Okay. So I'm drawing. I have a graph here on the right-hand side, right? Okay. So here is my graph. Okay. And obviously, this branch cut has to be on the complex Argand plane, right? Where you have a real and imaginary axis for a complex number. Okay, so real of Z, and you have imaginary of Z. Okay, let's see if anyone's coming in. Good, we have one person. Hello. All right, so we have the real and imaginary axis. Maybe we have some curve, right? So let me just draw a curve here. Maybe doesn't matter. I'm just not being accurate here. I'm just putting a random curve. The point is, a branch cut is a type of curve on the real and imaginary axis, and it has to be a multi-valued function. Okay, so you want to go from multi-valued to single-valued type of function here. Okay. All right. So that's what a branch cut is. Okay, that's a branch cut. Now, I'm going to bring up a branch point. Now, I can explain what a branch point is, but they have such a good definition over here that I want to bring up And then I'll explain conceptually what it means, but the way they've worded it is extremely good. 1 second. Yeah, I had it here. It was really good what they had for explanation for branch point. Of a branch point. Okay, so we're going to look at a branch point. Branch point. Okay. Yes, I think we're going to use this. Yeah, I think we're going to use. Yeah, I think we can do that. Yeah, this is a good definition that they have. That's really good for branch points. Okay, so we're going to talk about branch points now. So a branch point, right? So let me just put here a branch point. Branch point. Okay, so a branch point. I'm going to highlight this. I'm going slow, by the way, on this because until we understand what a branch point and a branch cut is, we can't even go through the theory yet. I need to go through the terminology first, right? Otherwise, the theory is going to be alien language. So these two words are very important, and we have to understand them deeply, what the meanings are, right? So a branch point, okay? Yeah, they have a very good one here. Yeah, so pretty much it's a branch point is pretty much the location or coordinate, right? So a branch point, so let me put over here, branch point is the location, right? Is the, I should subdivide these, otherwise it looks like they're continuations. These are different. Well, they depend on each other. Why am I saying depend on each other? But I'm putting a different definition here. A branch point is the location or coordinate, the coordinate, 1 second, the coordinate. Coordinate, anyone have questions? Anyone have questions? Don't be shy, put down questions. I'm always open to questions, okay? So a branch point is the coordinate or location. Of where multi-valued, I should say, where multi-valued. Yeah, let's look at a multi-valued functions. Okay, so functions meet. Okay. And when I mean multi-valued functions, just like root z, log z, and z to the m, z to the power of m over n, where m and n are, is a fraction. Okay, that's a fractional exponent. So a branch point is the coordinate / location where multi-valued functions meet. Okay. Anyone has any questions? Please let me know. All right, thumbs up, thumbs down if you're understanding. Thumbs up if you're understanding. Thumbs down if not. You want me to explain something. Okay. Just want to see if anyone else is coming in. Also, it's the Christmas holiday now, so probably people are winding things down when it comes to school and what they need help in and what they want to learn, or if they want to learn. Even if they're not students, there's always people who want to learn stuff. Usually they calm it down during the Christmas holidays. Let me see here. No, I don't see anyone coming in. Not at the moment. Is anyone coming in? Again, for anyone coming in, this is a live show, right? Today is contour integration masterclass. Okay, we're going deep into the theory today. Okay, theory more than example problems, right? Because I realize that this is a common area where people have trouble with integration, this type of integration anyways. That's what I'm talking about at a conceptual level. Okay. All right. So that's why I'm talking about contour integration, because it's quite often very, it can be a bit tricky to understand conceptually. So I'm going through it. Okay. So looks like we can continue, right? So pretty much, as I said, it's where different points It's where the functions, different branches come together. Okay, so for instance, right, where the branch point is just the coordinate / location where the functions meet. This means the same thing. Okay, so I'm going to give you an example of branch points and branch cuts here. I'm going to go to the graph on the side. Okay. Okay, so we have this graph here. Okay, so here's the graph. Again, it needs to be on the real and imaginary axes. Okay, so real, but we're in the complex plane, so we have the real on the x-axis, on the x-axis, imaginary on y. Okay. All right. And what we do when it comes to a branch point, it could be, that's just a point, right? So maybe it's located on the imaginary axis, somewhere on the imaginary axis, right? Somewhere here or on the positive imaginary axis, negative imaginary axis. They're just points, right? Where branch cut is the curve, okay? All right. Now, for the branch point, okay, for the branch point, we're just looking at looking at certain types of singularities and stuff like that. Okay, but I'll talk about that at some point, right? So if you have a branch point, okay, a branch point, actually, I'll go directly to the theorems now, I think. Yeah, I'm going to use that second drawing there, that graph, to discuss what I'm going to talk about next. Okay, so I talked about branch cuts and branch points, branch cuts and branch points. Okay, so that was definition one. Actually, you know what? I'm gonna erase this right now. Yeah, I should say something better here. Okay, so yeah, so that was it. So that was for branch cuts. As I say, definition 2 for branch points. Okay, yeah, otherwise it doesn't look accurate. So let's subdividing this. Okay, so let me just erase this. So a branch point, right? Definition 2. DEFN for definition 2. Okay, so this is now branch point. Okay. Again, I'm going slow for 2 reasons today because of the fact that we're learning contour integration from a conceptual level. Okay, so I want to go slow, make sure anyone understands. Okay, ask questions if you need it. The questions are handy. Okay, so we're looking at the definition of branch points, right? It's pretty much it says itself. A branch point is a coordinate. Okay, so branch point. There's a branch. 1 second here. I'll put, let's say, yellow. A branch point. So a branch point. Branch point is a common specific location. Location where multi-valued functions meet. Where multi-valued functions. 1 second here. Functions meet. And I talked about what multi-valued functions are, right? Above, right? All right, so if you look at, for instance, let me give you an example. A very good one would have been root z, right? Root z is a multi-valued function, so it would be looking like this, right? That's root z, right? Another one would have been log z, okay? So log z would have been like something like this because it's asymptote on the vertical axis. So log z is asymptotic to it. And this would have been log z, and so forth. Those are examples of multi-valued functions. And as I said, all they are is to the common specific location where those multi-valued functions meet. Okay. All right. Any questions? Anybody in the chat? Any questions on multi-valued functions? Multi-valued functions, what a branch cut or branch point is. Again, anyone coming in, we're talking about contour integration, right? From a conceptual level. And then we're going to do some basic examples and also cool simulations of the geometry of how contour integration works. Okay. So both from a linguistic and a geometric perspective of understanding what contour integration is. All right. Just want to see if anyone else is coming in, because I don't want to go too fast. I like to go at the pace if other people are coming in. Okay. So let me give you examples. If you looked at, for instance, the complex curve, as I mentioned here, root z, right? That I've put here, root z. Okay. Root z, let's say I said this is equal to some function. So w is equal to root z. W as a function of z equals root z, complex number z, by the way. Well, pretty much it requires multiple sheets, multiple branches, okay? Branches to represent. So there's two seats for root z. At the branch points of 0 and infinity. Okay, so there's a branch point at 0 and infinity. Well, can anyone guess why there's a branch point at 0 and infinity for root z? There's a branch point at 0 and infinity for root z. Anyone know why? There's a branch point at z equals 0 and z is approaching infinity. I don't like to say z is infinity. Z is over, you can't equal infinity when you approach it. Anyone know? Branch points at 0 and infinity. Well, root z, if you're under the square root, right, of z, z has to be equal to 0, right? Okay, so there's a branch point right here. Okay, so let me locate it. Here is the branch point. Yay, for root z, right? Maybe I'm going to highlight this as the red curve. No, let's use blue because it's overlapping. This blue curve here for root z, okay, which is w of z in green, highlighting green is equal to root z. But there's a branch point at the location 0. That's a branch point. Okay, that's why I said there's a branch point that's equal to 0. So that's an example of exactly what a branch point is. Now the branch cut, as I mentioned, is just the curve, the multi-value curve. Okay. All right, so we're talking about that, the branch points. Okay. Now, so that was a branch point. I gave you a graphical description of what a branch point is. Okay. All right, so we know the branch point. The branch cut is just those curves, the multi-value curves. W of z is root z, log z. It doesn't matter. There's more of these. It doesn't have to be just these two. There's multiple amounts of them. Okay. All right, so we talked about branch points and branch cuts. If there's no objections, I think we can start discussing something interesting. All right. Number 2 on today's list. Okay. Yay, we're trying to make math great again, guys. Help you. We're going to make math great again. All right, so we're going to be looking at number 2 of the menu, which is Pohl's residue theorems, residues and theorems on contour integration. Now that we know what a branch point and a branch cut is. Okay. All right, so anyone coming in, again, this is on contour integration. This is going to be a back and forth, right? Back and forth live show. Ask me questions, ask me anything highly related to the stuff that I'm discussing. Okay. Anything of that nature, anything conceptually that you have trouble with. All right. Okay, so we're going to be looking at poles, residues, and theorems for contour integration. This will help increase your mathematical toolkit. Okay. All right, so we're going to look at definition 1. As long as there's no misconceptions of what a branch point and a branch cut is. Okay. Please let me know if there's misconceptions, right? Because if there's misconceptions, then it's going to be hard to understand the meaning of the definitions that I'm going to put up. Okay, so if there's no, I'm going to look in the YouTube chat. If there's no issue, I think everything's okay. Someone said something. Okay, so let's look at definition 1. Okay, definition 1 for a contour integral of a function f of z. Okay, so if you have a contour integral of a function f of z, this is definition 1. Okay, function of a complex number z along a path. I'm going to call my path gamma. Okay, so gamma is a path. Okay, a path gamma, and it has some type of parameterization. Okay, if the contour gamma is then parameterized, okay, so gamma has to be parameterized. Let's see anyone's here. Okay. If gamma is parameterized by z of t, okay, for t belonging to the closed interval a comma b, right? The formula now becomes the integral over the contour gamma of the function of z dz, and it's equal to the integral from point A to point B of f as a function of z of t, right, times z prime of t dz, right? The z prime of t dz is the differential that we're dealing with, okay? All right, so that's what we have here. I'm going to highlight this formula, okay? So we've got this. Let's put this here. Okay, so highlight is very important. Contour, the definition of a contour integral. Does anyone have questions? So contour integral, okay. So contour integral of a function f of z along a path, some path called gamma, right? So gamma is a path, is a parameterization. I'll repeat again, right? Is a parameterization, okay? If the contour gamma, right, is parameterized by z of t for t belonging to the closed interval, right, square brackets, as long as t belongs to the closed interval of a comma b, and the formula is the integral over the contour of f of z dz is equal to the definite integral from a to b of f of z of t times z prime of t dz. Any questions? Who has questions? Not at the moment. Okay, so no one at the moment yet. All right. Okay, so we looked at definition 1 when it comes to contour integrals, the definition of what are contour integrals. Okay. All right, so please let me know if there's any issue. Okay. If there's any issue with this, please let me know in the chat. I like when people talk. Okay, don't be shy. Okay. So this is definition 1. Again, contour integral of a function f of z along a path gamma. I can call it whatever I want. I call it gamma in this case. Is a parameterization if the contour gamma is parameterized by z of t for t belonging to a comma b in the closed brackets, and the formula for any contour integral is written as the integral over contour, the path, that's what I mean, right? The path gamma of f of z dz, definite integral from a to b f of z of t times z prime of t dz. Okay. Okay. Make sure everyone's understanding what I'm talking about. Okay. All right. So, by the way, if you can put thumbs up in the chat, that'll be handy to make sure you're understanding what's going on. Anyone who's here, please put thumbs up and make so that's why I know if I can continue, or you want me to go back to something that isn't that you're not understanding in the definition. Maybe a word, maybe a phrase. want to make sure. Okay, so not one yet. Okay, so now we're looking at theorem, the first theorem, okay, for contour integration, which is very important. Okay, and that's called Cauchy's integral theorem. Okay. Now, Cauchy's integral theorem states the following. All right. If a function f of z, right? If f of z is analytic, right? So if f of z is analytic in a simply connected region omega, right? If a region is connected, right? So that means this connects there. Simply connected region omega, then the integral of f of z, the integral of f of z around any closed contour, right? So contours, by the way, somebody mentioned what contour is. So a contour, usually we have three or four types of contours. We can either have upper semicircles, lower semicircles, rectangles, key type of contours, and stuff like that. Okay. Most common one used are these ones. Let me put over here. So when I'm talking about contours, let me put an example. Okay, so an example of contours. You go here, example. Use a different color. It's very example. Example of contours. Okay. Let's say I have on the real and imaginary axis a upper semicircle that I chose. Okay. And let's say from here, since it's a semicircle, we have radius minus r and r here. Okay. All right, so we have minus r to r. Okay. And my semicircle, let's say, for instance, so it travels, right, along so our parameterization, you just put over here, parameterization starts from the minus r, right, from minus r to r, okay, like this. This is an example of one of the contours I'm talking about, upper semicircle. So we have to go along from minus r to r horizontally, right, go linear to the real axis, okay, and then its circles head back like this. Okay, so let me talk about. Okay, so that's my upper semicircle, and you can see the trajectory is going like this, right? So it goes from minus r to r, and then after it goes up like this from r to minus r. Okay, quite often when we do these integrals, we have to say that we have to go from a certain type of framework, right? Quite often for upper and lower semicircles, we go from minus r to r, and then we go from r to minus r. Right? Okay. All right. So that's how this is an example of one contour. Another one might be a rectangle, and so forth. Okay. Now you may be asking, how do we know what's contour to deal with when we're integrating? I'll discuss that hopefully at some point of this lecture. It's important, okay? But I can let you know, usually when it's when you have to choose semicircles, it's easier to choose when the function's in the form 1 over x squared plus a squared, usually is a semicircle. And you're probably asking why? Why, when it's like that, it's a semicircle? That just has to do with the fact that when you do contour integration, you want to avoid branch cuts. Okay. So if you avoid where your branch cut is, it turns out it's most effective if it's in the form 1 over x squared plus a squared, where a is a number. Okay. Oh, hi, Awfully. Thanks for coming in. What's your major? You must be a undergraduate student. Tell me a bit about yourself. I'm curious. I was willing to learn from different people. But yeah, I appreciate that you like the chat, like what I'm doing. It's a lot of work. Doing a math channel on YouTube is a lot of work, especially if you want to make it really good. This is nothing yet. It gets more interesting. Even for people who don't understand it, you'll like, if you like art and geometry, have a interesting thing for you guys. When just to show you guys how I can bring math alive, and also conceptually, for those of you who know at least integral calculus, this will help, the geometry will help you conceptually understand how to do these problems, okay? Oh, you're a chemistry person. Okay. All right. So, well, you still need math. It's not like chemistry has no math. But the level of rigor probably may not be this, unless you're in graduate school, I'm assuming. If you did a master's in chemistry, they will go into, especially if you do quantum chemistry and stuff like that, it gets more mathematically intense, possibly differential equations. I don't know the type of differential equations you do, but differential equations for sure, especially if you were to deal with Schrodinger. If you ever heard of the yeah, something's wrong with my tongue today. Schrodinger's equation and stuff like that, time dependent and time independent Schrodinger equations. For quantum chemistry, then math becomes important because you need to know differential equations and integration at a pretty high level. Okay, so this may or may not pertain to you, but if you plan to go further in your studies, you may end up doing this in late graduate school, right? Late graduate school, you'll probably be doing this stuff. If not, but it's definitely for math, physics, and engineering majors more so, because mathematically, this stuff is they need it more, right? They need it a lot more than chemistry guys. But thank you though. Thank you for coming in. I hope you subscribe. Okay, I appreciate it. I appreciate you watching the content. Okay. So, and let me know if you have any questions. If anything pertains to you, I'm sure you've done some form of integration, so you may understand some of the things that I'm saying for your chemistry classes. Just let me know if you've done. Oh, integrals. They were pretty hard, you're saying? The integrals per C? I'm assuming that's what you're. Yeah, they can be. Yeah, integrals can be tough. Yeah, and the reason why they're tough is because there's the mathematical method. You have to know when to use the correct mathematical method or integral method for each situation, right? Okay. So obviously, if you've done like things like, integrating by power function, integrating by U substitution, that type of stuff, you need to make sure you're able to make a distinction between when to use what. Okay. And it's not always as easy. It comes after doing a lot of practice. And when I mean a lot of practice, I mean a lot of practice. Okay. You have to do a lot of practice, and then after it sort of starts to integrate, pun intended, by the way, if that makes sense. Okay, you have to do a lot of practice. Oh, the triple and double intervals. Used to be watching some of my past live. I have live lectures, and also you can still watch the lives if you haven't seen them, and or my streams. Okay, my streams. I was talking about double integrals, right? I had to use a double integral for one of my last ones. I did something called the Gaussian integral, actually, which required us for integrating over the bell curve, e to the negative x squared, which you can't integrate that normally using single variable calculus because there's no differential to integrate e to the negative x squared. So we define it on a polar coordinates. And then what we had to do is we had to transverse the single integral to a double integral. And it's good because you're practicing your limits of integration on in polar coordinates and stuff like that, right? Yeah, quite often that gives people a hard time. Okay. It does give people a hard time. Double and triple integrals does give people a hard time. I mean, yeah, it does give people a hard time, right? I'm sure it's the limits of integration that's giving you the hard time, right? Yeah. Right. So yeah, double and triple integrals can be annoying. The best way to handle them, I can give you some like a short thing here of how to approach double integrals at least, right? For instance, if you had, right, some sort of plane, let me just move over here because I always like to help, even if it's not something that's completely relevant, right? I like to help when I can. Okay, so let's see here. So if you have a plane, okay, XY, right? So XY plane, and I have something like this. I have a curve like this. Okay, so maybe I have a curve. Just give me a sec here. Let's say y equals root x. Let's say I have another curve down here. Actually, this one will be y equals x. Okay, something like this. Okay, so this is y equals x. Y equals x. And let's say they asked find, right? So find or calculate the double integral over the region of dA, for instance, like this thing. Okay. Okay. Yes. Yeah. I'm going to try and do this. This is a classic example. Okay. So let's say you want to calculate the double integral over the region of dA. Okay. So if you look at calculating something like this, right? Okay. You have the two regions, y equals root x and y equals x. Okay. Now, first off, since it's written as a differential with respect to the area, right? This can be rewritten like this. Okay, so let me just do this first. I'm going to go over r of, let's say, dy dx. Okay. All right. So that's the first thing. I can interchange dx dy, but if I do, my limits of integration will vary. Okay. All right. So let's say if we want to integrate, so the inner integral is going to be with respect to y. Okay. So we're going in the y-axis. Okay. So if we were to do that, right? Now, be careful. It's with respect to y. Okay. So if it's with respect to y, okay, that means my upper and lower limits of integration, right? Right. Y1, let's say y1 is here and y2 is here, right? So it's the upper and lower limit of integration. These have to be as functions of x, if that makes sense. You know what I mean? Because the upper and lower are y's, right? Because with respect to y, it has to be a function of x. Now, what we do is we go from the lower curve, okay? Let me just highlight this. We go from the lower curve, okay, which is this guy here that I'm highlighting, the red curve here. I'm highlighting yellow. Okay, this guy here. We go from the lower, and then we go up. Okay, so what I mean by that is start here, y equals x, and then we go to root x. Okay, so y equals x to root x. It's our dy element. Okay, you understand what I mean? Okay, so my lower limit of integration would have to be x. You see what I'm doing? Right? My lower limit of integration has to be x based on the geometry of the shape here, right? Because the lower curve is y equals x. The upper curve is y equals root x. Okay, so my lower limit has to be x. Okay, my upper limit of integration for y has to be root x. Okay, any questions on what I am talking about? Hey, just another new guy. It's good to see you. I was I was just about to, I was thinking, where is he? Because usually I came on a bit late, but thanks for stopping by. I really appreciate coming in and help the channel. I appreciate it. And you're doing really well. You seem to be understanding the concepts really well. Oh, very good question. Very good question. Off glee xy. So if the value of a double integral is 0, does it necessarily mean that the function f of xy is 0 everywhere on the region D? No, not necessarily. No, it doesn't. Right? Because if the function, right? So if you have a double integral, right, and it's 0, okay, all it means, right? It could mean a number of things, right? Let's say you had a line integral, okay? If you have a line integral by, let's say, I know I'm getting to vectors and stuff like that, okay? So let's say we had something like this. You've probably seen this before, line integrals of a vector field f dot dr, right? Okay, line integral f dot dr, okay? And this is also equal to Green's theorem, right? Green's theorem is a double integral of what is it again? I'm trying to remember. Di p x minus di q di y dx dy, right? Okay, dx dy, all right? Since the line integral of f dot dr is equal to this, that's what the definition of line integral is. You can use Green's theorem to solve it, okay? A line integral is 0 when it loops back, right? So you may have a parameterization of your curve like this, okay? And it may start from point A to point B, right? So from point A, right? And then it goes around, right? Back to point B. And let's say point A and point B are the same, right? This means that this integral will be 0 because the line integral loops back again. So that will be equal to 0, means the double integral will be equal to 0 by Green's theorem. So what does that tell you? You see what I mean? Right? So the parameterization, that was an example of a parameterization, right? Of a line integral, right? And a line integral is equal to a double integral. And that double integral, actually, this is an example where you can have a double integral being 0, right? If the parameterization of your line integral, right, of f dot dr, right, is starting from, let's say, point A, and unfortunately, let's say it goes back to point B, this would actually be a loop, right? So we actually put a loop here, and we actually say that this would be equal to 0, right? This line integral will be 0, okay? Right? Which means that this double integral is 0 because this line integral, f dot dr, can be calculated by using Green's theorem, which is a double integral of, so a double integral can be 0. It just means that it's just looping back, if that makes sense. Okay, is that okay, Ockley? All right, any questions? I want to make sure I'm understanding. Is that good, Ockley? Let me know. Okay, so that's all. That's what it is. Now, if you have a function, right? If you have a function like this guy right here, right? Obviously, this would not be 0, right? I think you can figure out why. Okay, so no, it doesn't mean that. Doesn't mean that you're going to have so positive and negative values cancel each other out. Yeah. Yes. Yeah, exactly. Okay, that's right. Maybe that they have to cancel, right? So if you have, for instance, right? So if you have for here, for instance, trying to think of an actual example that would work in this present situation. I think an example on the top of my head. Come on, I think. If we had f dot dr, we're just using a regular curve like the ones I have. Y equals root x, y equals x, y is equal to Well, they have to be the same in order for them to cancel. That's just because they're opposite doesn't mean they cancel. They have to be the same but opposite, if that makes sense, right? Okay, so let's say if I were doing this, let's say if I was doing this double integral right now, okay, and let's say for instance, if I made it y equals root x and y equals negative root x for the bounds, okay, let me just think, and I integrated with respect to y, then I get y, because the integral of dy is y, then I take the upper limit of integration, and then it becomes a substitute for root x, minus root x, upper and lower limits. So no, it doesn't have to do with the upper and lower limits. It just has to do, because if you had the opposite, if this was root x and this was minus root x, no, that will not result in 0. So it doesn't mean they have to be the same and opposite. It just means that I'm talking about the path of the parameterization itself has to be equal and opposite, right? So maybe if you had something like this, right? If you had a line integral of f dot dr resulting in 0, then you'd have to have a sum of C1s and C2s of parameterizations, right? C1s and C2s and C3s such that they cancel and equal to 0, right? But not the upper and lower limits of integration like the curves. Okay? Right, does that make sense? Right, any questions on that? Okay. So we were just talking about, so no questions. I'll come back to you in a second once you've thought about it. But we're going to continue talking about contour integration. If x, y equals x, then the domain equals 0. F of x, y is x. Okay. And d is minus 1 to 1. Let me see that. I'm going to try that right now because I can't think of an example at the moment. But since you brought an example up, that's good. Sometimes I can't always bring up examples at the top of my head, but we can test that. Let me do that right now. Let's go over here. Yeah, so you just want a regular region. Okay, so not vector field. Okay, so let's move this over. Okay, so let me just make some room. Just making some room here. Okay, so looking at the double integral, right? So we're going to integrate. Okay, so we're taking the double integral, the region of f of x, y, dx, dy, and we're looking at integrating this guy right here. Okay, f of x, y is x. Okay, so x, dx, dy, limits of integration are minus 1, 1. Yeah, minus 1, 1, and then minus 1, 1 again. So let me just put that up. Minus 1, 1. So minus 1, 1, minus 1, 1. Okay, so if we integrated that, right? So just do integral from minus 1 to 1 of dy, integrate from minus 1 to 1 of dx, dx. Okay, so if we did that, this now becomes y from minus 1 to 1 times integral of x dx becomes 1/2 x squared from minus 1 to 1. Okay, so this becomes 1 minus 1 on this side over here. This will become 1/2. So 1 squared, minus, right? So be careful, minus 1 squared, right? We're just using fundamental theorem of calculus 2. You'll notice that this becomes 2. You'll notice that this over here becomes 2 times 1/2 times 1 minus 1. So yes, this there is a cancellation here. Okay. Yeah, it looks like my here. Yeah, because that's positive. Yes, it's positive. So yeah, this gave us a 0. Okay. The upper and lower limits of integration seem to be canceling out here, but this is not always the case. It could just be the, let me think here. It's the function f of x, y was x. If the function was not that, it wouldn't have canceled out. Let me see, would have. x1 minus 1. No, we're going to cancel out. Okay, so yeah, it's depending on the function. I haven't tested that myself, actually. That's why it's curious that I brought this up, that you brought this up. But no, there's a cancellation here based off the type of function. So it depends on the function. Okay, right. If there was no x involved, and we just integrated the double integral dx dy, then I get integral that would be x, and after limits of integration from minus 1 to 1 would be 1 minus 1 would be positive 2. So obviously there wouldn't be, that would be a non-zero number for the entire double integral. But since we've done it like this, we're integrating with over x, right? So x, this becomes 1/2 x squared. This now becomes 1 squared minus 1 squared. Okay, so this, since we integrated this, became a positive, an even type of exponent, and then that made it positive 1, right? Because even exponents make it positive. So this subtracts to 0. Okay, so it depends on the function. Okay, right. So when it comes to double integrals, it depends on the function that was already given. If it's going to result in the entire double integral being 0. Okay. All right. You understand? So the type of function that is given, right? Okay. Type of function that is given will determine if you're getting your value to be 0 for your entire double integral, I mean. Okay. Right? Because if you added different values, so it's not the limits of integration if they're equal and opposite. That doesn't mean automatically it's going to be 0. It depends on the function that is given. Okay, so make that distinction. Okay. So it's important to make that distinction right there. All right. The region, you said, yes. So the region, I believe you were asking earlier, does it mean that the function f(x) is 0 everywhere in the region D? Yeah. So the region, right? The region, let me think of that, because it's 0. Yes, that means that it has, yeah, in that case, yeah, it would have to be 0 everywhere in the region. Okay, because our double integral is calculating a type of area, if you can think of it that way, right? So if our double integral happens to be 0 for every region, this, in reality, if our integral is 0, that means that it's telling us that the area has to be a 0 in total, right? So in the entire region, right, the entire region would have to be resulting 0 everywhere in the region D. Okay. Is that okay? All right. So we've got over here, right? Let's go back here, unless there's a question, right? So the entire regions to be 0, right? Because we're taking a double integral, and we found that our double integral is 0, right? So the entire region, inside that region, the area has to be 0 everywhere. Okay. Yes. That's exactly what I'm talking about. Yeah. Yes. Yeah. That's right. Okay. All right. So let's get back. Let me get back to it awfully, because at the same time, I'll come back and forth if you have any questions. All right. So we're going to talk about something that is highly related to multivariable calculus. As I mentioned, we're looking at poles, residues, and theorems. All right. So again, we're talking about contour integration. This is a live masterclass on residue calculus. Okay. So residue calculus, as I mentioned, right, is a way to calculate very advanced integrals, right, that can't be solved by elementary methods. Okay. Right. So we're looking today, right, on contour integrals. But before we do that, we need to understand what branch cuts and branch points are. Okay. So for those of you coming in, I'll go through the definitions again. Okay, what a branch cut is. You need to know what a branch cut and a branch point is in order to understand residue calculus or contour integration. So a branch cut, I've written it here, is a type of cut which is used for multi-valued functions. Okay. So if there's any questions of that, please stop me. Right. So a branch cut is a type of cut which is used for multi-valued functions. What I mean multi-valued, I'm talking root z, log z, z to some fractional value, and so on. Okay. All right. So these are multi-valued functions. Okay. And the point of the branch cut is to take a multi-valued function and convert it to a single valued function. Okay. So I gave an example of that. And this is on the complex plane because contour integration is on a complex plane. Okay. So on a complex plane, we have the real and the imaginary axes. I'm sure you guys understand what I'm talking about. Real and imaginary axes. Put thumbs up if you understand what I'm talking about. You guys should know this, okay? So real and imaginary axes, okay? So on the real and imaginary axis, we're going to graph our guys here, right? So we have W of Z, for instance, root Z. It's supposed to be that blue curve here starting at 0, 0 at the origin because it's root Z, a root Z function, okay? And I also have log Z, which is this guy here, going up like that, right? Now, it is asymptotic, right? It's asymptotic. So be slightly closer to the asymptote that I put here, right? Because log Z has an asymptote right on the y-axis, okay? All right, so we have that. So these are examples of branch cuts, right? A branch cut is a type of multi-value curve that is converted to a single valued function, okay? All right. So we're looking at branch cuts, okay? And it's going to be very handy to understand branch points, okay? So I'm going to go and talk about branch points as well, okay? So branch point, right, pretty much is a common specific location where multi-valued functions meet. So if you have multiple branch cuts, okay? Let's say you had one branch cut W of Z equals root Z on the complex plane. And let's say you had, this is a bad example because this is asymptotic, so they're not meeting exactly at this point at 0, right? Okay. By the way, W of Z equaling root Z has a branch point at 0. That's why I highlighted red here. If you can see it, I'm going to zoom in that red dot there. At Z equals 0, that's a branch point of root Z. Okay. Does anyone understand why root Z has a branch point at Z equals 0? Why does W of Z equaling root Z have a branch point at 0? Just take the square root function, how the square root function is behaving. Okay, square root function is always greater or equal to 0. Okay, since Z is greater or equal to 0, you know that your Z has to be 0. So that's a branch point automatically. Okay, so automatically we have a branch point there. Okay, now a branch cut. Right, so we're talking about, let me see here, where are we? Yeah, branch points, right? So branch point is the common location where the multi-valued functions meet. Okay, so if you have W of Z equals root Z, I might use a better one instead of log Z because log Z is not meeting at that point 0, 0 there. I want to make it better. My mistake, guys. Okay, so here's W of Z. W of Z equals root Z, that's fine. Okay, if I had taken another type of curve, let's say x cubed, so you have a multi-valued function, okay? So you have another function x cubed, something like this. They meet at 0, 0. So they have a common branch point. Does that make sense? Because they both meet at 0, 0. So if I had W of Z equal to Z cubed, right? There's a common branch point of 0 located there at Z equals 0. Okay? All right. So I hope that makes sense. So for those of you who are new, never seen this before, well, guess what? I'm increasing your mathematical toolkit by teaching you contour integration. This will be handy for math, physics, and engineering majors who want to, as I said, increase your mathematical toolkit, especially as you get into higher years in math and physics courses. Integration starts becoming very important, and sometimes it gets very complex. So these methods will be handy in your physics and engineering classes. Okay. So again, I talked about branch cut, right? Branch cuts, type of curves, multi-value curves, multi-value functions that are converted to single-valued functions. And so like W of Z is like Q, W of Z equals root of Z. And a branch point is a common location, specific location where the two branch cuts meet at a specific point, okay? All right, so we're going to use this knowledge to understand our definitions and theorems on contour integration, okay? So let's get to it. Let's talk about some interesting stuff here, guys. So we're going to look at poles, residues, and theorems, okay? So a contour integral, what is that? What is a contour integral? How is this helping us? So a contour integral, if you look here, I'm going to zoom in. Don't have the same font as above. Sorry about that, guys. Definition one, contour integral of a function f of z, which is along a path I'm going to call gamma. Okay, gamma is some sort of contour for our parameterization. Okay, so we have a path called gamma, right? That gamma is our contour that we're going to have, right? If the contour gamma is going to become parameterized, okay, if it becomes parameterized by z of t, right, for t belonging to the closed interval a comma b, the formula is now the integral over path gamma of f of z dz is the integral from a to b f as a function of z of t, z prime of t, d. Slight mistake here. This would be a dt. Yeah, this needs to be a t. Yeah, dt. Okay, any questions on definition one? Anyone have anything interesting? For those of you who like integration and like learning new things, this will be fun, okay? But we do have to go through theory first because without understanding theory, the problems don't mean anything. Theory, quite often, that's another thing too with math. If you don't understand something, like when you're doing the homework problems, means that you haven't understood the theory good enough, and you have to keep going back. I like to always iterate that. If you misunderstand or conceptually having problems, it usually has to do with misunderstanding the theory or some geometric misunderstandings, usually one of these two things when it comes to the problem. So make sure you're always rereading definitions and translating the definitions. Sometimes you can translate the definitions into drawings and it makes more sense out of it conceptually. Okay. All right. Yeah. Oh, very good questions. Yeah, very good question. Yeah, I'm getting to that in a second. So a branch cut is necessary to define a single value for a log function, right? Because of the fact that, well, log, right? For instance, let me go over here, okay? We know how log looks like, okay? Okay, so log, so let me just write over here. Something like that. This is log z, okay? Log z has an asymptote. It's not the fact that it has an asymptote why we have to call it a branch cut. The definition of a branch cut is a multi-valued function. Okay. All right. So what I mean by multi-valued? What do I mean by multi-valued? You know what I mean? Well, first off, log z, right? Log z has to do with the fact that when you deal with functions, you're getting an x and a y value, okay? to get to a single valued function, okay, pretty much you're just doing what? What are you doing when you have a single valued function? Ugly. Let me know. What's a single valued function? Let me see if you're saying anything. Okay. All right. So, as I said, the point of using log here, right, and to get it to be a single valued function is the fact that what I mean by that is that we're going to be able to integrate over a single variable function. Okay, that's the only point of this. Okay, we're going to take the multi-valued functions and be able to integrate over a single variable function. Okay, so like integrating over real numbers or complex numbers in one variable. Okay, but these functions are called multi-valued because they have, let's say you have, in this case, you have a z and you have a w of z, for instance. Okay, this is one value, right? This is another value. Input and output of functions, right? Right. So you have, let's see, a z and a w of z coordinate system. Okay. And the z and w of z, right? When we have to deal with doing contour integration, right? We're only looking for a one output, right? Like when we integrate something, we just get one value, right? We're not getting two values. Where if we deal with a function, let's say f of x is y, right? We have an input, we have an output, right? Like in a coordinate system when we're dealing with something, whereas with integration, we're not. So it's pretty much things that you already know, just with different terminology, okay? But for complex planes, if that makes sense. Yeah. Now, what you're talking about there, can the branch cut be chosen more than one way then? Yes. Yes, it can. Yes. Now, that has to do with the type of when you do the contour integration. So what I mean is, point of contour integration is to integrate over a path in which you're avoiding your branch cut. Okay, so depending on your contour that you've chosen, maybe it's a semicircle contour, maybe it's a rectangle, doesn't matter what it is, you want to be able to avoid your branch cut. So you have to choose the correct geometric contour to do that. So that will vary how you deal with your branch cuts, right? So you can have more than one way of dealing with branch cuts, right? But typically you want to avoid branch cuts when you're integrating over a contour, okay? I'm going to get into that, all right? So you want to be able to always integrate. I should have written that down. Maybe you can put a note of that. Always integrate outside, like around the branch, not on the branch cut. That can be problematic. Okay. And that usually results in more than one way with dealing with the branch cuts, right? All right. So let's continue here. So we have branch points. And as I mentioned, the branch point is a common specific location, okay, where these functions meet, if you know what I mean, right? So as I mentioned, I gave you an example of, let's say, w of z is z cubed and w of z being root z. They have a common point at 0, 0. When z is 0, that was a branch point, for instance, okay? And so on. And there's other branch points, but at z equals 0 is a common branch point. I highlighted it in red. I think it's overlaying here. If you can see it, right? Okay, so that's what we've got right there, right? Okay, so again, So if everything is clear, let me know if everything's clear here. I can move into definition 1 and reiterate what I mean here. Okay. Is everything okay? All right, so we got that. All right, so we're going to look at definition 1 again, just to make sure. I'm trying to go slow, make sure everyone's on the same page. So a contour integral of a function f of z along a path gamma, okay, is a parameterization if the contour gamma is parameterized by z of t for t belonging to the closed interval a and b, and the following formula below has to be used. Okay, all right. Okay, good. Yes, I hope. Yeah, it's cleared things up. Thank you. Yeah, I just want to make sure that everyone's on the same page, because otherwise it's like, if I keep going, like understanding the definitions, like the words are more important than the equations, because if you understand the words, then everything else is just, it doesn't make sense. Okay, so as I mentioned, right, contour integral of a function along the path gamma is a parameterization if the contour gamma is parameterized by z of t. So the gamma is parameterized by a function z of t, where t is a parameter, okay? T belongs to the closed interval a and b, and the formula is this guy right here, okay? This guy right here is the formula that we're going to be commonly being used, okay? So this guy right here. All right. And for those of you who have taken multivariable calculus, you probably notice that this integral looks very familiar. That's right. And if you're thinking of integrals of vector fields, when you had to choose a correct parameterization, it's related to that, but it has nothing to do with vector fields. But it's related in the sense to that type of concept, because when you dealt with the vector fields, you had to there's a theorem on vector fields that says that if you take the line integral of f dot dr, where f is a vector field, and you take the sum of all the integrals along the path of parameterizations, let's say c1, c2, c3, then it's equal to the integral of f dot dr over c, right? So in terms of paths, yes, the path type of thing, like we're going to talk about that, but no, there's no vector field here, okay? Hope that makes sense. Okay, so we're going to move on from that. So that's definition 1. This is pretty much saying how a contour integral looks like when you're doing questions, okay? Now, theorem 1 is Cauchy's integral theorem. Now, Cauchy's integral theorem states the following. If a function f of z is analytic, right? Analytic, okay? And a simply connected region. This means that you have a region, right? And there's no holes, no discontinuity. There's nothing like broken. There's nothing broken about the region. Okay, there's no disconnect whatsoever, right? So if you have a region, right? So you have a region like this. Then you go over here. Okay, so let's say I have a region omega. Region omega is this green region here. Okay. So that's an example of the region. The integral of the function, right, around any closed contour in omega. Now, what I mean in omega, I don't mean on omega. Okay, I mean having some closed contour. Let's say, let me think of a contour. Any closed contour. Pi minus pi. Let me think here. If there's a subdivision, if we had a closed contour like this, some sort of circle, okay, right, something like that, circular contour, contour C, right? I'm going to call this C in omega. Then it's automatically 0. Okay. All right. So it's loop integral or it's contour integral. That loop there for the integral means that it's closed. F of z dz over c has to be 0 because we have a closed contour in omega. Okay. So the c that I've chosen inside of omega, right, is a closed contour. Okay, I hope that makes sense. All right. Okay, so we have that. If there's any questions on this? Any questions on this theorem here? I know some of these can get a little technical. Okay, if any questions at the moment? Yes. I don't see yet. Okay, so again, theorem 1 states Cauchy's integral theorem, right? If a function f of z is analytic in a simply connected region omega. Okay, so the region omega I've highlighted in green outside, right? Okay, and the integral of f of z around any closed contour. So contour is the shape that we've chosen, right? Contour C, right? So this is my contour C. Okay. When any closed contour C in omega automatically has to be 0. Right? That's what Cauchy's integral theorem states. Okay, any question on that? All right. Okay, so Cauchy's integral theorem. Now, then there is theorem 2 on Cauchy's integral theorem. Okay, this is a generalization, okay, of the integral theorem above. However, though, this generalization says when we have a function that has an isolated singularity, right, inside the contour C. When I mean isolated singularity, that's another thing I want to discuss here that I forgot about. I talked about Brandt's points. I talked about Brandt's cuts. A singularity is what happens in the denominator. Okay, so for instance, if you have something like this, let's say you have a function f of z equals 1 all over z minus z0, the singularity is this. Now, I know a lot of you are thinking of restrictions. Restrictions are not singularities. Okay, singularities have to deal with the poles, right? And poles are located by restricting this guy. So what you would do is you would say, quite often you're going to have functions like these when doing contour integration. So you're going to have something, let's say 1 over z minus z0, set z minus z0 equal to 0. Okay, what you will do then is solve for z equals z0. And this z0 is your pole. Okay. All right. So a singularity, to evaluate the singularities, okay, is just taking what's in the denominator of your complex function and restricting it to 0. Setting it to 0, and then solving for z. All right. Any questions? Can be analytic everywhere inside and on the closed contour. Oh, yes. Well, if it's not, pretty much what you're going to have is an issue with the connectivity, right? The connectivity of your region. Okay, let me go back here. Okay. Right, so if you look at the region omega, right, this guy over here, okay, right, if it doesn't have, as you said here, right, if the function is not analytic everywhere inside and on the closed contour, okay, then this guy can't be 0. Okay, so if this integral can't be 0, right, then we've got an issue, and the issue is the fact that if this integral f of z dz cannot equal to 0, right, then this is a violation of Cauchy's theorem. Okay, it automatically has to be 0, right? That's why it's essential, right, for the function to be analytic everywhere inside and on the contour, right? Because it's not if it's not in and on the contour, then we can't have Cauchy's integral theorem, right? It would be violated. Okay. Right? And the reason why it's violated is because the integral of f of z dz, right, right, is equal to, I'm going to get to that. There's something called the residue theorem. That's what I said bring up. you would get the residue theorem states that this line integral is equal to 2 pi I times the summation of all residues. And you would have residues inside of your contour. Okay, so remember, right, as I said, you have a contour inside of omega, and the residues inside your contour will result in non-zero values. And those non-zero values multiplied by 2 pi I will give you a non-zero value, and that non-zero value is equal to the contour integral, right? This contour integral. But then that will not equal to zero, and that will be a direct violation of Cauchy's integral theorem. So it has to do with something called the residue theorem. That a residue theorem states that you have to take all non-singular poles. As I mentioned, I was talking about poles over here, right? By looking at the denominator. And if your poles lie inside of your chosen contour, okay? If the poles lie inside your chosen contour, you sum them up, okay? But if you sum up your poles, they won't give you they'll give you a non-zero value, and that non-zero value is equivalent to this integral definition, okay? And as you can see here, this will violate Cauchy's integral theorem. So it needs to be analytic. It's analytic if you have, as I said, residues that are residues that are giving you a non-zero value. I'm going to talk about residues below. Okay. Yeah, I'm throwing a lot. As I mentioned, it makes more sense when you see more theorems. Okay. I'm going through the theorems. Just hang on. All right. So yeah, I'm just going to go through the theorems. Okay. And then hopefully it starts to connect more. Right. Once you see some of the stuff, you're going to say, oh, this 2 pi I came out of somewhere. Oh, that's why it's non-zero. Oh, why this is equal to 2 pi I or whatever. Right. Okay. So I'm continuing on. Right. So as I said, Cauchy's integral theorem states that the function f of z is analytic, simply kinetic region in omega, then the integral of f of z around any closed contour c in omega has to be 0. Okay. This one is important. Cauchy's integral theorem part 2. Okay. All right, so it's Cauchy's integral theorem part 2. So I want to make sure everyone in the chat is following. Okay. Now, this is when you have the case that when you have a generalization. Okay. So when a function, okay, has an isolated singularity inside the contour C, and that means that it's in your contour, right? So it may be inside some type of contour. By the way, when I mean contour, I'm talking about this. Okay, quite often the contours that you need to know are semicircles, rectangles, and stuff like that. Those are the most commonly chosen contours. And so let me just put it over here. Okay, so let's say from minus R to R, minus R to R. So if you have a semicircle, and we know every circle has radius R, right? Now, if you have quite often we have to split them up into semicircles upper, semicircles lower, semicircles. We choose which one if we're dealing with a positive or negative integral. So I'm choosing it. Let's say I use an upper semicircle. We still have a radius, right, on the real axis, on the x-axis here, as I mentioned. Now, from minus R to R. Okay, so we go, here's how our parameterization works. Okay, so I'm just draw something here if I can. Is there yellow? I might use green. No, let's use blue to hide, or red. So what we do is, for our parameterization, okay, we first travel along the line that is collinear to the real axis. Okay, this right here that I've highlighted. So we go from minus R to R on a semicircle. And then we trace back from R to minus R, which is the upper arc of the semicircle. Okay. Oh, this contour here. Yeah, so this contour here, if we were to integrate, no, it would not be considered a closed contour. No. And the reason for that is because we get a non-zero value if we were to integrate over this contour. This would not be exactly a closed contour. Okay? A closed contour would be something that is, let's say, let me think of a closed one. If you have a circle of, if we did something in the circle, let me think. That's a good question. If you have a circle and I've bounded it, if I bounded it from minus, let me think of that one. Let me think. Oh, silly. I'm being silly. My mistake. Yeah, it is a closed contour. Yes, this is a closed contour, right? Because the contour is bounded. What I mean by bounded is I start from minus r to r and then go back from r to negative r, right? So it loops back. It loops back again and again. Now, as I mentioned, just because it's a closed contour doesn't mean, right? Doesn't mean that this will result by Cauchy's integral theorem to be 0, because it needs to follow it being analytic and simply connected. Okay? If it's not analytic and simply connected, then it will result in a non-zero integral. Okay? Right? That makes sense? Right, so it depends on if it's analytic and simply connected, but it is a closed contour, as you can see, right? This is closed, right? The semicircle is just because it's bounded, right? There's no open part here, right? Because there's a line here that we have along the parameterization, and after it goes up on the upper arc. Okay, all right, does that make sense? All right, so that's why. Okay, so it's a closed. It's to be closed. The closed contour. Okay. All right. So theorem 2 now, right? Right. So we have theorem 2. Theorem 2. Let's see what time it is. Theorem 2 is a generalization when a function has an isolated singularity. Okay. That means that it's inside of the contour, right? Maybe my singularity is here, or here, or here. It cannot be down here if I've chosen an upper semicircle contour, right? The point, right? The singularity has to be inside the contour for theorem 2 to make sense. Okay, so when a function has an isolated singularity inside the contour C, by the way, this is C, okay, right? That's C, right? Inside the contour C, if f of z is analytic everywhere and on the contour, right? Theorem 2, you have to be careful, and on the contour C, except at z0 inside z, then the integral of f of z over z minus z0 is this guy right here. Okay. All right. So the thing that I highlighted here is very important. So again, right, if f of z is analytic everywhere, inside, so it has to be analytic inside here, okay? See, analytic here. Inside and on the contour, that means even on, like on the path, right? And on the contour C, except at a point Z0. That means everywhere except for these parts here, right? These parts here are the poles, and Z0 it represents the pole, or the singularity, you can say. And the singularity can be determined by doing, as I said here, that I've highlighted, f of z equals 1 over z minus z0, restrict z minus z0 to 0, right, in the denominator, because there's a singularity, right? That's what a singularity is, setting it to 0, solving for z equals 0. Z0 is the pole, and Z0, if it's a pole, that means it's just that specific point on our plane, right? But as it says here, it has to be inside and on the contour C. Otherwise, this theorem will not apply, right? And I'll also mention this, except at the point Z0. Okay, so as I highlighted here, if one of these Z0s, it has to be analog everywhere except at Z0. Okay, but let me a start point and a finish point to be the same. Start point and finish point to be the same. What do you mean, like the R's and minus R's? What do you mean by that? Start point and finish point. That I'm not understanding quite. The start point and finish point to be the same. To understand what you mean. Which start point? Do you mean like from minus R to R? R to negative? That's what I'm not understanding. Yeah, I'm not understanding quite what you mean. So look, the closed contour must start and end at the same point. No? Yeah. Yes. And that's why I said it's closed, right? Because this closed contour here, right? As I mentioned, right? What you do is you go from minus R to R, from the minus R to R on the real axis, right? And then you're circling back here, right? So you go from, when integrating along a semicircle, whether it's upper or lower, you go from minus R to R, and then from R to minus R, right? So let me put it like this: minus R to R on the line, okay? On the line here, on the real axis, okay, that I've highlighted, along this parameterization here, from minus R to R. Then you go from, then, let me put over here, then if along R to minus R for the other part of the parameterization, right? So R to minus R on the arc of the parameterization, arc of the parameterization. That's how it works for contour integration. Doesn't have to do anything to do with them starting back at the same point. You're just starting from wherever you started from, right? And then you circle back to the starting point in order for it to be considered closed. Okay. Yeah, exactly. Now you're understanding. And that's why I'm putting this here. Like if you've noticed in a lot of my notations for these contour integrals, I put a loop here because that's what I'm saying, right? That's exactly what I'm saying, is that it's a loop. Right? And hence the word, the definition of a loop integral, right? There's a loop around this integral here. Hope that's making more sense. Okay. Now, any question about okay, good. I think you're getting it. All right. Okay, so then we also have theorem 3, Cauchy's integral formula. Now, this is Cauchy's integral formula, not his integral theorems. Integral theorems 1 and 2 are, okay, not the same, but Cauchy's integral formula is identical to integral theorem part 2, as you can see, right? Okay, and this theorem won't be used hardly that much. It's not that important. This theorem extends to higher order derivatives of f of z, right? So it just says if you have a loop integral, a contour integral of f of z dz all over z minus z0 to the n plus 1 power, it's just 2 pi I over n factorial times fn of z0, where n is depending on what derivative you have, right? First order, second order, third order. Okay, so I make sure everyone's getting that, right? Fn of z0 is the nth derivative, right? Of f evaluated at z0, right? Z0 means exactly where it's been evaluated. Okay. All right. So that's what we got here. All right. And then we have any questions on that? Question. Yeah, that's what I mean. Yeah, that's exactly what I'm saying. Yeah, that's what I'm saying, right? That's why it's a loop. That's what a loop is. Okay, that's exactly what a loop is. Good questions, by the way, awfully. Very good questions. Yeah, very good questions. All right, so if there's not any other questions, don't think there is, we'll continue. All right. Now, theorem 4, theorem 3, I mean, even if I didn't put it there, it's not useful. It's good to have it in your toolkit, but it's not as important as theorem 4. I want you guys to pay attention to theorem 4. This is the most important theorem in all of contour integration. I'm going to highlight this. Okay, I'm putting an asterisk here. You can't draw an asterisk now. Asterisk. This is so important. Theorem 4, okay? Oh, thank you, awfully. I appreciate that. I really do appreciate that. Thank you. It means a lot. Yeah, I try my best, right? So I like to explain things deeply. Okay. As you can see, I haven't even started a problem because I want to really go through the conceptualization of this section. Okay, because without the theory, without deeply understanding the theory, the problems you're just going to go in circles with the problems. Okay, unfortunately, that's the reality with math. Is like every time if you have trouble with a question or whatever, more likely it's like you don't understand the theory. Now you always have to go back to it. So I'm putting a heavy amount of time in this lecture on theory. Okay. All right. I hope you guys are ready for theorem 4. Okay. Theorem 4 is really interesting. It's called the residue theorem. And this is something I was talking about earlier, but I'm going to come to it right now. Okay. Now, I hope you guys can see it. It's at the bottom of my screen here. Can you guys see theorem 4? Please let me know if you can see the theorem. It's very important. Can you guys see the theorem? Hope it's okay. I'm assuming you guys can see it. Okay. Right? So it's just saying for evaluating complicated, it's a way for evaluating complicated integrals, obviously, but it states that the integral, right? It's just saying that the integral of a function, f of z, right? So a function of a complex number z, around a simple closed contour, and when I mean closed contour, I mean C, is just this, right? It's the loop integral of f of z dz is equal to a quantity of 2 pi I multiplied by the summation from k equals 1 to n of the residue of f of z sub k, comma zk. Now, this will make more sense when I discuss residue calculations. Okay, residue calculation formulas, because this is saying the summation of residues. Okay, now a residue, right, is, I'm going to explain what it is, and then I'm going to refer back to this. Okay, so I'm going to go back and forth. Okay, good. I'm glad you can see it. I believe that's excellent. So I'm going to come back to this in a second. Just give me a moment. Okay, so I'm going to come back to that. What page was I on again? No, that's not it. That's not it. That's not it. That's not it. Yeah, residue calculation formulas. Okay, so definition 1 of residue calculation formulas. So a residue is defined by this formula right here. Okay. I'm going to explain what pole of order 1 means. That means that this guy here is raised to degree n, and n is a pole. So if you have n being 1, that's order 1. N is 2, that's a second pole. 3, third pole. Okay. So this is of order 1. If you have an order 1 pole, a residue is defined by this formula right here. So the residue of f comma z0, where z0 is the pole. Remember, a pole is by taking the denominator of the complex function, setting it equal to 0, solving for z, and so forth, right? But z equals z0 is a classic example. That's the most basic one. Residue of f comma z0 is equal to the limit as z approaches the pole there, z0, of z minus z0 times f of z. Okay, I hope this is making sense for you guys. Okay. All right. So again, this is the residue calculation formula for a pole of order 1, right? This is the definition of residue for pole of order 1. This is an important formula, okay? And it will be used in calculating the residue theorem, okay? So what you do is when you have a problem, okay, and you have to get its singularities, you have to evaluate the singularities. So again, 1 over z minus z0 is a classic example of a complex function, okay? Evaluate the singularity. That means there's a restriction in the denominator that has to equal to 0. Solve for z, you get your z0 or your a value. When I mean z0 or a, I mean a number, okay? And once you've gotten that, you've gotten your pole value, okay? Then you plug in your poles into your residues. Depending on the number of poles you have, you calculate your residues, okay, using this formula. And then you go back here, sorry about that. You go back here and use theorem 4 and you sum up all your residues. I hope that makes sense, okay? You sum up your residues using this formula down here. Any questions, please? Okay, I hope I made that clear. You sum up your residues. Okay. Right, so you have to sum up your residues, and that will give you, exactly what you have to do, right? So you have to sum up all your residues, and that will give you the integral that you're looking for, your loop integral, because quite often we'll be calculating a loop integral, right? Or a real integral, okay? But that's how you do it. You sum up all your residues that you got from your poles/singularities, and that is it. That's what the residue theorem states, okay? All right, any questions? Oh, when is the residue theorem used, right? That's what you mean, right? When is the residue theorem used? Okay, so the residue theorem is used every time when you have to use contour integration to calculate something. I'm going to give you an example right now, right? We're ready for examples, okay? So I'll give you this example. Let's say we wanted to calculate this integral right here, dz over z minus a. Okay, dz over z minus a. This is supposed to equal some constant of 2 pi times I. Okay, so 2 pi I. I'm going to explain why that's the case. Okay, first off, the way to approach this is to do this. Okay, so the solution, I'm going to highlight solution. Now, what we need to do, right? What we need to do is do the following, okay? Look for the singularities, right? So since we have our function, right, f of z equals 1 all over z minus a, okay? So I'm going to show you why the residue theorem is used here. 1 over z minus a. I'm going to have to make more room. Ah, damn it, for my next example. I hate when that happens. I try to predict enough space, but I don't have the space. Damn it. Let me just make some room here. Sorry, guys. That's going to be, for example, 2. Hopefully, I think this is good enough. I'll move it down even further. Damn it. Just one sec. The example. I'm going to look at that after. That's where I'm going to integrate this guy, minus infinity to infinity of dx all over x squared plus 1. Okay, so we're looking at this guy right here. So 1 over z minus a is our f of z. Okay, that's my f of z, right? How do I know that's my f of z? Because we know that a contour integral along C of f of z dz, so it's written like this. And that means that my f of z is this 1 over z minus a. Okay, so f of z is 1 over z minus a is the complex function. Next thing I have to do is find the singularities. Set z minus a equal to 0. Okay, solve for z. So z is equal to a plus 0. That's just z equals a. Okay, that's my pole. So once I figure out what my z is, equal to some number A. That's my pole, okay? Then from the pole, use residue theorem, okay? Residue theorem stated the following. I'm just going to refer back to it. Just give me 1 sec. 1 second, I decided here. That's not it. Where's my residue theorem? Yeah, this guy over here. Residue of f comma z0 is equal to the limit at z approaches z0 of z minus z0 of f of z0. That's, now remember that this is only for pole of order 1. What I mean by pole of order 1 is that the function here is of degree 1. So we use residue calculation for pole of order 1. Okay, so I'm going to do this now, right? Just 1 second. So z equals a. Okay, so I know I have to use this formula. So residue of f comma z0 is equal to limit as z approaches z0, okay, of z minus z0 times f of z, that formula. All right, so following so far? Okay, so we have this. Then this is going to give me, right, let's plug in the pole, z approaches z0, that is a. This becomes z minus a, z0 is a, right? Okay, so that's my value. F of z, we said, was 1 over z minus a. Multiply this by 1 over z minus a. I'm just going to leave this on the side for now. I wanted to make space for that. I'll just leave that later, okay, because I need the space. This is equal to 1 because these cancel. So now I have the limit as z approaches a of 1. Limit of a constant is 1. So now I get the residue of f comma z0. Since this was my only pole, I only have to evaluate one limit. Okay, now I can use my residue theorem. So next, by the residue theorem, it states that the loop integral of f of z dz is equal to 2 pi I times summation from index k equals 1 to n of the residue of f comma z sub k. Okay. All right, you see what I mean? Okay, because I want to evaluate this integral, and the integral that we're looking for was this guy here, dz divided by z minus a, the complex integral. So this becomes 2 pi I times the summation of this. Summation of this is just this residue. We only had one residue that we had to calculate because we only have one pole. So 2 pi I times 1, and that gives us 2 pi I, and that verifies why this is equal to 2 pi I. Does that make sense? Okay. So the residue theorem is used to calculate all contour, like complex integrals, like complex integrals in terms of complex numbers z, but they can also be used for real integrals as well, right? We may have an integral that we don't know how to integrate in terms of elementary methods. As long as we convert the x's to z's, we can just apply contour integration using the residue theorem. Perfect. I'm glad you're enjoying this. Good, good, good. Okay. All right, so we have that. Excellent. I'm glad to hear that. Let's go to another example. The other example, I want to show you one on the real numbers. Okay, I had another one down here. Let's say I have to put some more space. No, I can use this as well. Integral of this, right? So example. So here's another example. So example. Example is this guy right here. Okay, if we want to integrate from minus infinity to infinity of dx divided by x squared plus 1. Okay. So if we want to integrate this, right, all we have to do, you'll notice automatically I can do the following, right? Actually, I'm going to need more space for this. Yeah, I'm going to have to go to another page here. Okay, so continuing, right? So we're integrating, so I'm just going to say continue. Continuing. If I have to integrate from minus infinity to infinity of dx divided by x squared plus 1, Well, what I can do is, right, I can transpose my f of x, which is 1 over x squared plus 1, as f of z, right? Notice that f of z is equal to 1 all over z squared plus 1. See what I mean? Okay, 1 over z squared plus 1. Now, what ends up happening here, okay, is we want to evaluate the singularities, right? So set z squared, I can put it in the middle here or something, maybe better. Set z squared plus 1 equal to 0. Obviously, if we did that, we get z squared is equal to -1. Z equals plus or minus I, because the square root of a -1 is the imaginary number I, and since it's a square root, it's plus or minus, right? Okay, so I hope that's making sense, right? So Z is equal to plus or minus I. Now, I'm going to draw my contour here. I didn't for the other one. I should have done it for both. I recommend all the time drawing your contour, and the reason why is because you need to know where your poles are located. If your pole is not located inside the contour, you don't add it to your summation of the residue theorem. Okay, this is very important. So again, if your pole is not inside of your contour, you can't add it in your summation. Okay, that's why you need to always be drawing geometric structure, the geometric model of your contour. Okay, I'm going to explain what I mean here, right? So since we're dealing with f of z equals 1 over z squared plus 1, the type of contour you want to choose is a semicircle. Okay, that's just how we do it. When you're dealing with anything in the form of 1 over z squared plus a squared, where a is a number, choose a semicircle. It's very easy to deal with just because of the fact that you're avoiding, you should be avoiding the branch cut of 1 all over z squared plus 1. Yeah, let me think, plus 1. Yeah, you'll be avoiding it, right? But it comes so axiomatic that people are like, okay, I see 1 over z squared plus a or whatever. I'm using a semicircle. Okay, so let me draw something here. Okay, so let me just draw a branch, not branch, but my contour. That's what I mean. Okay, so you have something like this. Okay, and we're going to choose a semicircle. So again, from minus r to r. So we first go along our parameterization, right? Parameterization of C is going along here. Okay, so from minus r to r, and then I go from the upper arc here of the semicircle from r to minus r. I like to make better semicircles. So annoying when I can't get them right, though. Ah, damn it. You know what I mean? Like this. Okay. So from minus r to r, and then from r to minus r. Okay. All right. So by doing that, we're going to get something interesting. Okay. You'll notice that if z equals plus or minus I, the pole that we get on the this is the imaginary axis, by the way. This is the real axis on the complex plane. Now, since z equals plus or minus I, we have a pole here. Let's say this is I on the positive imaginary axis, negative I outside. Since negative I is outside of the contour, we don't include it when we calculate using the residue theorem. So make sure you understand that. Negative I is outside of the contour, the semicircle, so we don't use it in our calculation. You understand? Okay, so when we do our calculation, right, first off, we have to use the limit formula, right, the residue calculation formula. Just 1 second. So that states that limit, so remember, residue res of f comma z0 is equal to the limit as z approaches z0 of z minus z0 of f of z. Don't worry, we're dealing with a degree 1 order pole because we dealt with z squared plus 1 to the first power. I'm only dealing with order 1 poles today. Okay, so we use this formula. We evaluate limit as z approaches I only because we have a non-singular pole here. A non-singular pole means that the pole is inside of the contour. If the pole is outside of the contour, we won't calculate its residue. Okay, so z approaches I. This becomes z minus I times f of z. F of z we say was 1 over z squared plus 1. However, though, this can be simplified. This can be factored. This is now limit as z approaches I of z minus I times 1 all over z plus I times z minus I, difference of squares here, right? Z squared plus 1, z plus I, z minus I. This was a z minus I cancel. I'm left with the limit as z approaches I of 1 all over z plus I. Okay. If I input my limit where z approaches I, this gives me 1 all over 2I for this limit. Okay, see what I mean? All right, so 1 over 2I. Then what I can do is, watch what happens. Something interesting happens. This is my only residue because it's inside of the contour. Now I can use the residue theorem. So by residue theorem, right? So I can say, remember, our contour integral over C of f of z dz is equal to 2 pi I, right? So I just smoothed over here, right? It's 2 pi I times summation from k equals 1 to n of the residue of f comma z sub k, right? This formula. So this is just 2 pi I times the summation. The only summation we're taking is this one because it's inside the contour. So residue of f comma, when I mean z0, I should be saying I, positive I here. So I'm just taking only the residue of the function f of z evaluated at I, the pole I. Okay, only that one, because the other one is outside of the contour. We don't add it. So then it becomes 2 pi I times 1 over 2I. 2's and 2's cancel. I and I cancels. This contour integral is pi. But since the contour integral is equivalent to this integral, because we can go from reals to imaginary back to real. So this integral from minus infinity to infinity of dx over x squared plus 1 is pi. Okay? And you can now evaluate real integrals using contour integrals. Pretty cool, huh? Any questions? Any questions at all? Yeah, it is. It is very comprehensive. Yeah, what's the question? Assume it's with the calculation that I just did. Please let me know what the question is. Mm-hmm. That's a brilliant question. Brilliant question. Yep. So that has two simple poles. Yeah, inside a closed contour like the one I have. If the residue at these poles are equal, so the residues are equal in magnitude, sure, but opposite in sign. What is the value of z? Yeah, well, it should be not like non. Doesn't mean that it's going to be. Doesn't mean that it's going to be 0. Okay, contour integration is not like that. All right, because when you have the poles, right? When you have the poles that are f of, as you mentioned, right? You have two simple poles, right, inside of the contour, right? And even if they're equal and opposite in magnitude, okay, it doesn't mean that it's going to be 0, right? Because there's a lot of factors that come involved, right? Actually, it can be it can also even be undefined in some cases, because based off what's canceling out in the factors from the residue calculations, right? Like the residue calculation where I talked about the limit of blah, 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 right? It doesn't mean that it has a specific value just because they're equal and opposite in contour integration. No. Okay. Because there's a lot of things that come into play. The order of the poles that you're dealing with, what's canceling out and stuff like that. That's what's going to dictate what's happening. So there's not a fixed value. But what it does tell us, though, is that you can have an undefined or infinite case. Yeah. I just can't think of when I'm going to have my infinite case, though. Can't think on the top of my head when we had the infinite case. Like if the denominator is undefined, I mean, like if it's 0 in the denominator, that would involve taking the limit. Let me think. Taking the limit of 1 over z minus 0. Z is equal to z is equal to I. Let's say z I. Yeah, negative I and I. No. Because then one would be. Because watch what would happen, right? Let's go back to the whiteboard. Right? So let's say, for instance, as I mentioned, right? If we evaluated, here's a classic case where we would have simple poles equal opposite in magnitude, right? One being plus I, one being negative I. Now, as I mentioned, another reason why having equal and opposite, poles does not necessarily doesn't give us 0, is because of the fact that, remember what I said, you can only use the residue theorem, this guy over here, okay, if and only if your pole is located inside of the contour. I is located inside the contour. Negative I is outside of the contour, okay? So if that's one reason, that's one of the reasons why it doesn't have a fixed value, and it's going to have a non-zero value because of the fact that if you use the residue calculations and the residue theorem, you're only choosing one of these poles. You can't choose both unless you had some sort of circle, right? You had a circle that enclosed both I and negative I, okay? And then you added their summation of the residues, right? But we never choose a full circle when it comes to doing these, right? When you have equal and opposite poles, because those poles, as I said, right, you're either going to choose one or the other, because quite often when we're using the contour, we're choosing either an upper or lower semicircle in the cases so far. So if you had equal and opposite contours, you're only choosing one of the poles. And since you're only choosing one of the poles, usually it should result in a non-zero either a non-zero value or an infinite, like you get some undefined value, I'm thinking, but that's it. Okay, you understand what I mean? All right. But it's a good question, though. It is a very good question. Yeah, but contour integration doesn't work that way. We don't take both the equal and opposite poles, right? Because the residue theorem says you only take the non-singular poles, right? That means poles that are inside of the contour that was drawn, and you sum up those inside, right? So if I had another pole here, for instance, maybe let's say 2i, let's say for instance, I found another one 2i, then I would add the residue calculation for this and this in here. You understand what I mean? In here, right? And that might give us, I don't know, like another, but it'll be a non-zero value. That's for sure. It'll be a non-zero value. Okay. Good. Excellent. Oh, yeah. Conceptually, you're getting it. Good. And yes, it is difficult. It's difficult and it's not difficult. It's difficult because it's very comprehensive. That's what's difficult about it. It just takes a lot of rigor. And I can also prove to you that this calculation is correct. Okay, that's where simulations come in. So I'm going to go to the desktop. Give me a moment. Okay, and I'm going to get out of share screen. Okay, so just give me a moment. I get out of share screen. Okay, and what I'm going to do is I am going to do something on my whiteboard on the desktop here. Okay, see if I can find it. Yeah, just give me a sec. I'm going to show you two simulations. Okay, I'm going to show you this one right here. Okay, hopefully you're able to see what I'm talking about. Just give me a moment. Okay, just give me a sec here. If I can share screen again. Share screen. Nope, that's not it. I have to go to... No, entire screen. Just use the window. Just give me a sec. I'm going to... Just give me a sec. I'm trying to share a screen of my desktop. I'm acting funny today. Just 1 second. Oh yeah, probably have to get out of that. Just give me 1 sec. For some reason, my desktop is acting funny. Okay, so I'm going to go to share. Nope. We're going to do the entire screen. Okay, hopefully you can see the desktop. Can you see the desktop? Please let me know if you can see the desktop, what I'm going to do, okay? Okay, so I'm going to show you the desktop. Okay, yes. So watch what happens. Here is the integral of dx over x squared plus 1. So I have a function 1 all over 1 plus x squared, right? This is the arctangent function. That's what it is. I integrate over it, and you can see that we get exactly pi. The simulation shows us. Okay? Really cool. So if you integrate from minus infinity to infinity of dx all over x squared plus 1, you get the value pi exactly. Okay? Yes. And there's two ways to do that. You could have done contour integration that I showed you, or you could have done regular integration of dx over x squared plus 1. Just notice that d by dx of arctan is equal to 1 over x squared plus 1. Integrate, and you get back to the way arctan of and that will give you pi, right? Well, arctan from minus infinity to infinity, so you'll take the limits of that from negative infinity, arctan infinity minus plus arctan of infinity, negative infinity gives you pi over 2 plus pi over 2 gives you pi. So it'll be something like that. Okay. So there's the curve there and the interval and the limit of the area. All right. All right, so I'm going to go back into the whiteboard. Okay, so back to whiteboard. Hope that makes sense. Okay. Now, I want to talk about common student mistakes. Okay, one thing is common student mistakes. Okay. Mistake number 1 is contour integration is about drawing clever paths. Okay, yes and no, mainly no, right? Contours are chosen by decay, and more than decay, they're chosen based off where you can avoid the branch cuts. Again, you want to choose your contour geometry such that you're avoiding the branch cut. So if you have a curve like this, for instance, maybe something like, I don't know, I'm trying to think of a curve. Maybe something like that. Let's say your branch cut is this. Right here is my branch cut. Okay, I want to avoid touching that branch cut. Okay, so I might choose something like, I don't know, an upper part, a lower part of my semicircle, right? Now I'm choosing the lower part of my semicircle. As you can see, having this type of parameterization for my contour is avoiding the branch cut. This yellow curve here is my branch cut. You understand? Oh, you're very welcome. You're very welcome. I'm glad you enjoyed it. Please stay tuned for more on my channel. I really appreciate it. Yes. And also, if you want to learn more on this stuff, I'm always available for one-on-one tutoring / consulting on this stuff, just to let you know. Okay. So if you want to learn more on it, I'm always available one-on-one. I can give you like practice problems, stuff like that. And then you can really accelerate in this stuff. It's always best one-on-one. You're very welcome, and I'll see you next time. Glad off me. I hope you like and subscribe, by the way. All right, have a good night. Okay, so yes, the branch cuts. All right, so that's the first thing. Mistake number 2 is that a residue is simply the coefficient of 1 over z minus 0 z0. The only a residue is simply the coefficient of 1 over z minus z0. That's what a residue is, right? So residues aren't formulas to memorize. They're just the coefficient of 1 over z minus z0. Okay, as I keep mentioning, that's very important for residues. Very important. And then we have mistake number 3. All singularities have the same. Yes, good night. Thank you. Thank you very much. Mistake number 3. All singularities behave the same. Poles, branch points, and essential singularities behave very, very differently, actually. Not even close to the same thing. So remember, mistake number 1, right? Contour integration is about clever paths. No, it's not. Contours are not chosen by the path. They're chosen by the decay. For example, this is showing decay, right? Now, why does the decay matter? Well, because quite often decay is avoiding the branch cut, and that's the whole point of contour integration, is to avoid the branch cut. Okay, so that's mistake number 1. Mistake number 2, residues are formulas to memorize. No, they're just coefficients of 1 over z minus z0. They're just coefficients of the residue calculation. Mistake number 3, all singularities behave the same. Nope. Poles, branch points, and essential singularities are all behave very differently, and there's no one fits all answer. That's not true. Okay. All right. So mistake 1, mistake 2, mistake 3. I hope you guys integrate this like conceptually. Okay. All right. So that's one thing I want to bring home. All right. So we've discussed 1, we've discussed 2, we've discussed 3, we've discussed 4, 5, 6, and 7. Yeah, we did a lot. And 8. And we finished 9. We had 2 students ask a bunch of questions. So that is it for tonight. We've completed everything. I think we are done. Okay, yeah, I think we're about done. I don't see anything else happen. All right, guys. I think I'm gonna call it a night. Again, if you want to catch me, my schedule is Wednesdays. Let me start again. Sundays, 7 p.m. Eastern time. Wednesdays, 8:30 p.m. Eastern time. Thursdays, 7 p.m. Eastern time. Okay. Wednesdays is the only live show. The other 2 are streams. All right. Just letting you know. So 1 stream, 2 streams, 1 live show. Okay. I think we're good. Yeah, I think that is it on our list tonight. So I was going to talk about, yeah, we're done. Let me see here. Nope. No. Yes. I don't see anything else on our list tonight. Okay, so if this moment on contour integration was something that finally stopped feeling like a headache, right? And and was much more than memorizing paths, and started feeling invitable and thing. That's my goal. My goal is to make this conceptually better, not by formulas, but by modeling and drawing and seeing how math works. Okay. So everything you saw tonight, everything, absolutely everything, decay, real integrals, complex integrals, poles, was developed in a rigorous step-by-step way from my book, Advanced Integration Techniques, where we look at applying integrals and mathematical methods. Okay. So that's one thing, right? So if you want to learn more on this topic, you can check my book in the description below, and the link will be in the description of this live show. And if you want to work through this material one-on-one and learn more specifically in the specific niche of mathematics, not just contour integration, but integral calculus in general, and other areas of math, I also mentor students, mainly undergraduate. That's my prime focus, is undergraduate students. Some grad students, not as much, but mainly undergraduate students. I'm always available. The link will be in the description of how you can reach me there as well. Okay. Have a good night. Today was very good. I will try to make a stream tomorrow, maybe not. I'm going to have an internet issue for the next few days, so I'll try my best. But if not, we'll just do it probably Sunday. That's the next stream, hopefully. All right, guys, have a good one. Bye for now.